We'll go through spatial weights. As I mentioned earlier, we'll look at two types of functionality. One is the cheater way. You make your weights in GeoDa and then you read them in. The other one is when you create the weights internally in PySAL. Then you still want to write them to a file because you don't want to redo this every time. So that's what these weights files are about. So we'll use quite a bit of functionality. We'll use NumPy, we'll use GeoPandas, we'll use a sample data set again. We'll use I/O to read the weights files, and we use the weights functionality from libpysal weights. So rather than writing each time libpysal weights, I will be writing just weights, right? And then this last thing is I discovered that NumPy 2.0 has this new way of if you do print the contents of an array, it does it differently from before. And I like the old way, so I put in the legacy. If you like the new way, you don't need this. Okay, we're good to go. A lot of functions. You can look at this from NumPy. We make an array, we get the mean, we get the standard deviation. I talked a little bit about flattening last week. I didn't mention the word flatten, but whether your array is an actual vector with 2 dimensions, row and column dimension, or an array where it only has 1 dimension, we'll read the file and set a variable to integer type to use as an index. We get the path, we open the file, and then this is all the functionality from the weights that we will be using. It looks like a lot, but it's actually pretty straightforward. For each observation, there's neighbors. For each of these neighbors, there's weights. You can row standardize the weights. That's a transformation. And then you can get all kinds of characteristics of the weights: minimum, maximum, mean, percent non-zero. We can make weights from different sources. We can make them from a GeoPandas data frame, and we can make them straight from a shapefile. So all these kinds of things are what I'll be talking about. Then we can make them symmetric. We can create weights on the fly for regular grids. We'll use that later when we do simulations. Create the weights for 20 by 20 grid. It's 1 line. As I said, in some instances, we will want the weights not in sparse format, but in full format, so we can turn them to full. And then lag spatial is the construction of a spatially lagged variable, which for each observation creates the average of the neighbors. And that will be the main tool through which we bring spatial interaction in a linear regression specification. So very important concept. I'm running ahead a little bit, just show you how you can make it, but we'll revisit this in a couple of weeks. So we will be using the Chicago sample for this. Again, as I mentioned, always the same setup. You specify everything you need in this one cell. So if you want to change anything, this is where you change it. And we'll start by reading the weights that we created in GeoDa. They're already there. They're part of the sample data set. And we will be using the weights class, which is the older one. In fact, it's the oldest one in GeoDa, in PySAL. First, I mean, if you want to work with spatial data, you need spatial weights. So one of the first things we developed was code to handle and create spatial weights. There's a newer one. It's called the graph class. It's not completely ready yet, so I don't want to talk about it. But by all means, if you want to check it out, check this link. And that's a different way. It does all the same things, but it uses a network graph way of thinking about it. So we start with the queen's weight. We're going to find the path. So in file Q is the name of the GAL file that has the queen contiguity weights. We use open. This is from libpysal IO, open with the path. We use read, and then we see what we have. And we have libpysal weights object. So this WQ is now a weights object. And what is in WQ, you can check that out with a dir command. But basically, what it has is a dictionary with, for every observation, the values, the keys. So every observation has a key. For every observation, we have the keys of the neighbors and the neighbors attribute of the dictionary. And we have the weights for those neighbors in the weights attribute of the dictionary. So we have the neighbors and we have the weights. Each of these are dictionaries. And to know what you have, I always find it useful to list the keys. So you turn the keys into a list and then you just see what we have. And this way, you can see whether these are characters, integers, codes, or whatever, right? A key in a dictionary can be anything. So but you have to know what it is. And then with each key is associated something else. And for example, with the key 1, the neighbors are given as the keys of the 6, 7 neighbors, as the case may be, right? So the neighbors are who the neighbors are. If you don't do it right, and this is kind of a gotcha in PySAL, you're in trouble. So you have to know what these keys are. And, like with any dictionary, you can pull out the keys. You can write code that is completely robust to this if you get the keys and then make sure you use those keys. But if you're just kind of checking it like I do, line by line, you may get into trouble if you think something is an integer, but it's actually a character and vice versa, right? It's very picky. So the weights then are all 1. They are initially 0, 1 weights, binary weights. Later, we'll see how to row standardize them. Okay. The weights object is very rich. It has all kinds of attributes already pre-computed. So when this is done on the fly as you create the weights object. So you read it from a text file, and then as the object is created in PySAL, all these things are calculated or deduced from the text file that is being read. 1 is the size, that's n. So if we want to know how many observations we have, we look at the attribute n. So notice I don't do print or anything like that. And this is where I ran into trouble with NumPy, right? That with the legacy way, it gives you 791. With the new way, it looks a little different. Okay. Then very important as I mentioned, you want to make sure that every observation has at least 1 neighbor. So we want to avoid having isolates or islands. How would you know that you have an island? I'm looking at the minimum neighbors, the maximum neighbors, the average neighbors, the percent non-zero. How many neighbors does an island have? And what would be the minimum number of neighbors? 0. Whenever you see a 0 there, you have trouble. Okay. Then you have to decide, what do I do with these islands? And you basically have 2 choices. One is you kick them out. It's not going to matter because they're not connected to anything else. So they do not feature in a computation of spatial autocorrelation or in a spatial regression. You might as well drop them. Okay. Or you make them connected. And you can do this very easily because these weights files are all text files. So in a simple text editor, you find the one that has no neighbors and you give it a neighbor. Is this okay? Depends on the context. I'll give you an example. In Detroit, nobody from Detroit, right? In my other class, there is somebody from Detroit. But there's an island. That's where the Renaissance Center is. It's in the middle of the Detroit River. So if you use a geographic characteristic touching borders, the island in the middle of the river doesn't touch any of the other census tracts. So it is an island. Do you want it to be an island? Not really, because it's very important in the economy of the city of Detroit. So you want to connect it to census tracts that are across the river, either connected by a bridge or by a tunnel or whatever, right? That's something you have to do by hand. Now you can because it's a text file. There's other tricks, you can work with buffers and things like that, so you can do it within the GIS as well. But the thing to keep in mind is that if you give the island a neighbor, let's say on the river border, then you also have to give that neighbor the island as a neighbor. You have to keep the symmetric relationship. And that's where it gets tricky. So if you do this editing, it's very easy to spot the ones that have no neighbor. You give them a neighbor or two neighbors, but then you have to make sure that you reverse that relationship somewhere else in the data set. So in this case, it turns out 1 to 18 number of neighbors. Symmetry, let's say you did do some manual editing, then there is no symmetry check per se, but you can check the number of asymmetric relationships. So if there aren't any, then you're fine. In a few minutes, we'll see an example where there are, and then you have to do something about it. Okay, K nearest neighbor weights. Yeah, you got a question? No, same thing, right? So I'll go pretty fast. You can go over this at your own pace, but this is always the same thing. We have the same number of observations. Okay. What's weird with this picture? Again, minimum number of neighbors, 6, maximum number of neighbors, 11. These are K nearest neighbor weights with 6 neighbors.
Shouldn't just be K to K, like each has?
It should be 6 and 6. Yeah. But I went really fast and I didn't tell you, these are K nearest neighbor weights that have been made symmetric. If you recall, for some things in spatial regression, specifically maximum likelihood methods, we need symmetric weights, intrinsically symmetric weights. K nearest neighbors are not, but you can make them symmetric. And so that's what we did here in GeoDa. In a few minutes, we'll do it in PySAL as well. So same thing, you can look at the neighbors. Some of the neighbors are the same with 6, but some now have more, like 8. Kernel weights, this is a tricky one. So I'll give you an example. We'll get back to this later, of a triangular function with variable bandwidth and k equal 10 nearest neighbors. So we read it and we open it, and then we look at what type it is, and we have a problem. It doesn't say it's kernel weights. This is a current issue with PySAL. It may be fixed by the time the quarter is over, but it's been in there for a while. PySAL doesn't know when it reads a kernel weights file. Okay, GeoDa does, PySAL doesn't. So we have, because for some in SPReg, the regression package, we will make robust standard errors, and they use kernel weights. And SPReg checks, are the weights kernel weights? And if we use these weights, it will say, no, these are not kernel weights. This doesn't work. But they are kernel weights. So we have to do something you should never do. And yeah, so the other function has the same problem. You can try this out yourself. You should do something that we will do something that you should never do unless you really know what you're doing, which I do, is so in Python, you have things called dunder attributes. Does anybody know what dunder attributes are in Python? They're double underline attributes. And so most object-oriented languages have hidden attributes of a class, so you can't see them from the outside. Python doesn't really have that, but it sort of fakes it by having these underline classes. And the double underline classes are a special type that you're supposed to never touch or see. So you should never do this unless you know exactly what you're doing. But I'm manually changing the class. Oops. Yeah, well. Okay. So now we're in business. So now when we do the robust regression, it will check the type of weights. It will say, oh, this is okay. Go ahead, right? Okay. So much for the GeoDa weights. Now in PySAL, there's all the functionality to create every weight you want, as long as you know the commands. And they're all very similar in structure. They're all part of libpysal weights. Then you specify a weights type, like queen or rook or KNN or kernel, and then from data frame or from shapefile, okay? And then there's some extra arguments, okay? For example, we get the shapefile, we turn it into GeoPandas data frame, we make sure we have an ID that is integer. This is just a fluke because it isn't an integer in this data set. And then here we go. Weights, queen, from data frame. This is the data frame that we use. And these are the IDs. And so we have a weights object. And then it's all the same. You can do this on your own. There's all the same characteristics as the one we had for GeoDa. One thing we haven't done yet is row standardization, which is very important for the regression. That is the transform command. So we're going to go control return, and the weights are no longer 1, 1, 1, but they've been divided by 7. Okay. You can write the weights file, then you can read it again. I leave this up to you to practice. It's pretty straightforward because I want to talk specifically about the special functions. KNN weights, same thing. You have to specify K. Otherwise, you see here, KNN from data frame, and you can check it yourself. It is the right type. KNN, it's not symmetric to begin with, and you can make it symmetric. Kernel weights, same thing. You pass it an array of X and Y coordinates that can be very general. And then you say what function it is, whether it's variable or fixed bandwidth, and so on. So this is all the same kind of setup. You know, you give the type of weight, you know, queen, KNN, kernel, from data frame or from shapefile, or for the kernel function, from an array of coordinates, and then you're in business. All the properties are the same in all these different forms. So you can try this out for practice. I do want to spend a little bit of time on these special operations. Okay, the first one is, and we'll use this a lot when we do simulations, it's how to create a weights file for regular grids. And that's a function called lat2w. And it takes two sizes, 2 dimensions, one for the row dimension, one from the column dimension, or if you wish, one for the horizontal dimension, one for the vertical dimension. So if we set grid size to 20, that's going to be a 20 by 20 grid. It has 400 observations. And so this command weights, because it's really lib PySAL weights, lat to w, 20, 20. Rook is for rook type weights. If you want queen, you say rook equal false. You don't say queen equal true. This is, just what it is. And then you get the queen weights. And so again, you can check on this. A grid cell for a rook weights has north, south, east, west. So rook weights on a regular grid have 4 neighbors, except on the edges. So the corner cells only have 2 neighbors, and then on the edges, they have 3 neighbors, because they're missing 1 dimension, either north, east, west, or south. Everything else has 4 neighbors. Queen weights on a regular grid have 8 neighbors, except again at the edges, where they have fewer. Okay, so that's lat to w. Then, did I make this one? So that is the weights full command, and you pass it a weights object. So this is the sparse weights object with the neighbors and the weights as a dictionary. And now we turn it into an array, a matrix actually. And let me see if this one, yeah. So one gotcha here is that this returns not one thing, but 2 things. And if you don't know this, it can be very confusing. I mean, I have to remind myself all the time. The first item is the actual array. The second item are the keys. So if you want the actual array, you have to take the element 0 of this tuple, or you do it like I do, where you set it up as a tuple, and the first one is the actual matrix, the second one is the keys. So you see this is a NumPy array that I just created, 791 by 791. And then the final item is the spatially lagged variables. We'll first make a column vector from this so it's the dependent variable we'll be using in some of the initial sample examples for regression analysis. I think it's years of lives lost or something. It's a health estimate. The larger the value, the worse. It's an indicator. So the mean is 5,017 roughly, and the variance is 3159. The command for the spatial lag for each observation is an average of the neighbors. The neighbors are defined by the weights matrix. The average is defined by the actual weights. Typically, they're the same, they're equal. Sometimes they won't be. If they have kernel weights, they won't be the same, but typically they are the same. All we do is for each observation, identify the neighbors, average the values. That's the spatially lagged variable. We see it has the same size. It has roughly the same mean. but it has a much smaller variance, which illustrates the smoothing effect that the spatial lag operator has. So the smoothing effect means there's less variability in the spatially lagged variable than there is in the original variable. Okay, we'll return to this later. You can also create it by just matrix multiplication right here. It's exactly the same result. In some instances, lag spatial is faster. Some instances, the straight multiplication is faster. This is not going to be an issue for you. It is an issue when you work with very large data sets. Then typically what you want to do is actually do a sparse matrix multiplication. But that's too technical for us for now. So I'm going to leave it at this. I know this went a little fast, but as when you look at the notebook, it's always the same thing, you know. So it's queen from shapefile, it's KNN from shapefile, it's kernel from shapefile, and from data frame, same thing. So it's always the same structure. All the weights have the same properties. They all have the neighbors dictionary, they have the weights dictionary, they have minimum, maximum, mean, percent non-zero. You can turn them into full matrices. You can make them symmetric. You can row standardize them. All this stuff is baked into the spatial weights object.